So this is in the section on the product rule. You could multiply this out, and then you just have a polynomial, which is straightforward, but takes a bit of work. So what we want is, you know, if this is f and this is g, y prime is f g prime plus g f prime. So we can just write it down. 10x squared plus 7x minus 2, that's f, times g prime. Well, we can look at this, and if you can't just kind of rattle off the derivative of something like this by now, you want to practice a little, right? 2 is 0, minus x squared, well, that'll become minus 2x. All right, that's fg. G is, of course, 2 minus x squared. And now again, you should be able to just rattle this off. 10x squared, well, derivative of x squared is 2x, so we have 20x plus 7x, that becomes plus 7, and the 2 becomes 0. Now, because in other classes you might have been expected to do more with this, I can understand if you thought, you know, do I have to try and simplify this or put it in standard form? But if the problem doesn't say so, this is the answer. Or if you can stop here. If the problem goes on and you're going to need this simplified, well, what's involved here? Minus 20. This is just an opportunity for me to make mistakes, but that's okay. Plus 14x minus 4 minus 10x to the 4th plus 7x cubed minus 2x squared. Is that clear? You don't need to do this. And then we do the same thing here. So 40x plus 14 minus 20x cubed minus 7x squared. Okay, so now I just have a bunch of terms. To avoid making mistakes, I like to distribute, you know, signs like this. So minus, minus, plus, minus, plus, and then I just have to, you know, go from left to right. I've got negative 10x to the 4th. I really like crossing things out because then I can't see what I have. Minus 20x cubed, minus 7, that's 27x cubed, minus 47x cubed. 2 and 7 is 9x squared. 40 and 14 is 54x. And 14 and minus 4, did I get everything? 10. This was unnecessary in this case. One thing one might want to do, not a guarantee, but you might want to do a simple check. You might want to say, if I plug in 0, what do I get? This is 0, and this is 14. Oh, did I write 10? I mean 14. 10. Oh, wait a minute. Huh. I'm suspicious. I think I must have made a mistake. See? You do a little, just a simple little check and you catch your errors. Okay, who had their hand up first? I don't, all right, we'll start over from there and we'll work our way, yes. Did you find my error?
A couple, yeah.
Oh, yeah, I'm really bad at the blackboard.
So, this one, I'm pretty sure it's negative 14x at the very beginning. Right there. And this is 7x times.
Yeah, yeah.
And then the 14x squared.
I'm sorry, 14 squared?
Yeah. Negative 7x times negative 2x.
Well, this is positive, right?
No, still on the 14x. Still on the 14x, because positive 7x times negative 2x.
Oh, another math mistake. All right. Yeah. So I need to go over and do it carefully without talking to 30 people and waving my hands. You know. No, probably 20% of the errors people get on exams is because they're a little nervous and they're having trouble focus. You guys, you have all that tension, you know, schoolwork, the world's going crazy, and math is hard and I hate it, or it's been bad to me. It's really hard to focus, but it's really important, you know, come in, be brave, take deep breaths, calm, and also do what I did, which is just, you know, do some kind of check if you can. Did I make a silly mistake? Because then you can go back and be more careful. Thank you. Did you see something else?
Yeah, just along the same lines as that. I'm curious, how did you get the like semi-quotient, negative 10x to the fourth plus
Oh.
negative 7x?
I probably made another mistake.
Got that from?
Yeah, where did that come from?
Because you just are supposed to like FOIL, right? It's just 2x times your 10x squared plus 7x minus 2 plus.
Gosh, you'd think I came to this class drunk. No, I'm not.
Just wanted to make sure.
All right, well, okay, so let me, at the risk of embarrassing myself even more, I'm going to stop talking to the class. I will talk out loud though. F times G prime, that's correct. G 20, that's correct. I can do calculus, I just can't do algebra. No, there was no x to the fourth.
14.
Hmm?
I'm just kidding.
Yeah, that's 14. So, okay, anybody see any, are you doing anything wrong there?
That's what I got.
Yeah, okay. Yeah. You know, again, it's practice, and it's also kind of state of mind. You know, get a good night's sleep before the midterm, come in, relax, you know, say one of those, what do they call those, you know, I can do it, I will do it. I'm smart and people like me. Yeah. All right. Any Other problems, questions about this? Yes?
It's not really that homework, but if this were to be on the exam, would it be okay for us to leave it like without distributing everything?
Yes. Absolutely. The only reason you need, I don't know why I did this, because I'm trying to take up time, because I'm hoping some students will show up. There might be a problem that's extended, like this might be the first part of a problem, and in order to get to the next part, you might have to distribute it, and then you would know you have to do it, but, you know, no, you don't have to simplify this, unless it said, which I wouldn't do, simplify this, then you would have to. Yes?
Can we do, let's see, page 197, like number 2 or something? Just like the differentiating string.
197, number 2. Okay. F of x equals tangent of x minus 4 sine x. Now, in the beginning, you look at this and you see like 3 or 4 different pieces of information you need to know. But as you get on, you can skip some of them. Like, I'm going to write it this way so I don't have to try and come up with a new statement. Some of the derivative of the sum is the sum of the derivative, right? You don't have to keep thinking that. You know, I can find the derivative of tan and I can find the derivative of sine of x. Constants, that's another rule. They don't matter, right? So what do I need to do this? I need to know the derivative of the tangent of x. Now, as a practical matter, that should be like burned into your head or at least put on your cheat sheet. But let's say you came into my exam and you forgot your cheat sheet and you forgot what this is, but you do remember your trigonometry, which says that the tangent is the sine over the cosine. Well, that's a quotient. So we can use the quotient rule. So what does the quotient rule tell us? Well, it's going to be the derivative of the sine. Maybe I should write this out. So hopefully you know that the derivative of the sine is the cosine times the sine, no, times the cosine, times g, minus the derivative of g, which is the cosine, which is negative sine, times sine, all over cosine squared. Well, all right. Now, yeah, you could leave it this way. Right. This is a plus. This is cosine squared plus sine squared, which is 1. So we get 1 over cosine squared. And, you know, that would be fine too. But if you remember, 1 over the cosine is the secant. Now you're a master. Okay, and that's just the first part, right? So we have secant squared x minus 4 times the derivative of the sine, which is the cosine. And we're done. Okay? All right. Was that? Can anyone tell me what homework number 3, what the pages were?
The derivative one?
Yeah. I think so. Because it says here that people had trouble with 23. Oh, is this one of the problems I gave you? E to the P? This is 189. Y equals e to the p, e plus p square root of p.
The derivative one I think you're talking about is on 163. It's
Oh.
21 on 163.
Oh, you think it's 150? Yeah, I don't think I gave you that problem. 153 or 160?
163.
Okay. Find the derivative using the definition. Oh, no, I wouldn't have done that. Did I give you that?
It's 181.
Hmm?
Page 181.
Wait, 180.
Oh, 182?
Oh, there's no 23 on 181.
Yeah, 182 from
182?
That sounds better. Okay. Differentiate the function. 22, 23. Really? Scratching my head. You could use the product rule. I mean, you could, and it works. You want to hammer in a nail, you could use your fist. It would hurt. But so what? Derivative here is going to be root f g is f prime g minus g prime f over g squared. So f prime, this is f, is 6x plus 1 times g minus g prime, that's 1, times f, all over p squared. So 6x squared plus x minus 3x squared minus x.
And the numerator is supposed to be 3x squared plus x cubed.
Yeah.
For the initial part of the problem. X cubed.
Oh, it's cubed.
Yeah.
Thank
No,
you.
no, 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 no.
X
X
cubed.
plus x cubed.
Oh, yeah, my sight isn't what it used to be. All right, let's fix that. 3x squared. Guess I can get rid of this. Okay. So, 6x squared plus 3x cubed minus 3x squared minus x cubed over x squared. So 3 minus 1 is 2x cubed, and 6 minus 3 is 3x squared over x squared. So it would be 2x plus 3. Does that sound right? Okay, but I didn't have to try and pound this nail in with my hand, I have a hammer. Except at 0, this is equal to 3x plus x squared. And its derivative is just 3 plus 2x. Much easier. Do I have a problem at 0 with the derivative? No, because the derivative is a limit that's, going to go to 0. And the derivative function is a limit. The limit will be defined there. It's a nice, smooth, continuous function. So all this, it didn't really help us anyway, right? If you prefer this, to warn you that you can't plug 0 into the derivative function. Okay. Other homework questions? Let's see. Oh. Well, my answer sheet for number 15 is wrong. If you want to look at my answer sheet. Looks like moot or hoot people got 19 wrong. I can't read it right. Number 19. So, number 19. X cubed times x plus 3. It's the same kind of question, even simpler. Time for a little weapon here. X plus 3. So again, we can use the product rule. F and this is G. So 3x squared times x plus 3 plus x cubed times, oh, it's just 1. And we get 3x cubed plus 9x plus x cubed, or 4x cubed plus 9x. Really? Yeah, I guess so. But in this case, it'd be much easier to just write this as x to the 4th plus 3x cubed. And we can see right away it's going to be 4x cubed plus 3 plus 9x squared. You don't have to do it the hard way. You're much better off, you're going to make fewer mistakes if you think a little, does it make sense to simplify it first? In this case, it certainly does. All right. Now this is a different assignment. She doesn't tell me which one it is. Many people did number 11 instead of 41 on page 93. Usually when that happens, it's because I made a mistake, not because you did. I'm not going to worry about something you did or didn't do. Number 35. Anybody have any idea which assignment 35 was on? What page? Could it be 189? Did I assign that?
Page 189.
Yeah, okay. I want to do this because what seems to happen on exams is people do the calculus just fine and forget their algebra. And still need to know algebra. So 35 says, find an equation of a tangent line. Let's see, this is 35 on 189. Find a tangent. Find the equation of tangent. Given y equals x squared over 1 plus x at the point 1 comma 1/2. Well, I think I've said this before. It's always a good idea to verify that this point is actually on the curve. If Stewart, there probably won't be a mistake, but if I write the problem, there could be. So what have we got? We've got 1/2 equals 1 over 1 plus 1. Check. That was easy. So we have some curve. I'm just making this up. And we have some point on it, and we want to find the, y equals mx plus b for this tangent line. We know at this point that we can find the slope by finding the derivative. So we want to find the derivative here. And we need to use the quotient rule. So squared prime times 1 plus x minus x squared times 1 plus x prime over 1 plus x squared. Right? I just wrote out the formula. Now I have to find the derivatives. 2x times 1 plus x minus x squared times 1 over 1 plus x squared. Now this is a perfect example of where simplifying is a waste of your time. We don't need to simplify it, we just need to plug in 1 to find our m, right, our slope. So what do we got? 2 times 2 minus 1 over 2 squared, 3/4. All right, at this point, we go back to high school algebra. We know that y equals 3/4 x plus b. So all we have to do is find b, and the information we have to find b is this point. Right? There's one point that we know. So y is 1/2 equals 3/4 times 1 plus b, or b equals 1/2 minus 3/4, which I think is negative 1/4. This is 2/4, 2 minus 3 is minus 1. So our solution is 3/4 x minus 1/4. You have to be able to do that with a line. Some of you with a little better memory than I might go, I didn't have to do that. I can just write down point slope form. So it's x minus 1 times the slope equals y minus 1/2. Okay, that's my slope, point slope form. That's the, will turn out to be the same, I hope. Okay. Other problems, more problems? Anybody else? Yes?
Page 197, 45.
197, number 45. So again, one nice thing about this segment here is you're probably getting a feel for what to expect on the exam, right? Mostly finding derivatives. Okay, I'm sorry, did you say 45 or 47?
45.
45. Find the limit. Right. I don't know what it is. I guess I'm getting all the... all the markers that are ready to die. I'm glad you asked about this one because it's typical of a certain kind of problem. Page 198, number 45. It seems tricky if you don't know the trick. The trick is very simple. Sine of 5x over 3x, right? You look at that and you go, it's too bad we're not about 5 chapters later where there's a really simple way to figure this out. We have to think a little more clearly. Well, let's start out with that 1/3. Get that out of the way. We know we can do this because constants move in and out of limits that way. It's one of the limit laws we looked at. But we don't know what this is. What we do know is that the limit as x approaches 0, sine of x over x is equal to 1. And that's going to help us. So what can we do to make this problem look like that? Well, let's do a substitution. Let's say u equal 5x. That's going to make this into sine of u. And we also know then x equals u over 5. So we substitute in. I'll leave this for last. This becomes sine of u. X becomes u over 5. Well, that's, that 5 can go here, and it can come back out here. And now this looks like what we want, but we have to just think a little bit here. If x is going to 0, and u is 5x, what is u going to? Well, it's going to 0. Right? What else could it be? So now we have the piece that we know. Limit as u goes to 0, sine of u over u is 1. And we have our constant. So this goes to 5/3. I would encourage you, if you have a calculator, graphing capabilities, plug it in, plug in your y. It's the electromagnetic fields. So Tuesday I brought this in and I pushed, I pushed on, nothing happened. I brought it home, I checked it worked. Now it didn't work, but now it works. Okay, so if you push the Y button, you can type in a formula. You can type in this formula, sine of 5x over 3x, and you can graph it. Look at the graph and you'll see that in fact it's going to cross the y-axis at about 5/3. So, it's a good way to check stuff. You're doing an exam and you come up with an answer, 7 or something, and, you plug it in your calculator and you see, no, I'm wrong, I have to rethink this. All right, other,
We have a question.
yes,
For number 35, how did you get 3/4 for the answer? How did you get 3/4? So like, yeah, from there. How'd you come up with 3/4?
now, everybody has their level. Some people just look at a problem and go, well, I see the answer is 5, or whatever. Don't feel there's anything wrong if you need to write it out. X is 1, right? So that's 2 times 1. 1 plus 1 minus 1 times 1. I'm exaggerating a little here, right? 1 plus 1, that's fine. Okay. So this is 2 times 2 minus 1, or 2 squared. 4 minus 1 is 3/4.
Oh, I get it.
Okay. Don't feel, everybody's at a different, level with this stuff. You just have to be able to do it. You don't have to, it's not some math competition where speed does not matter. Okay. Any other questions on homework? All right.
We have a question.
All right.
So, page 197, number 3.
Number 3.
Yeah.
Okay. So, y equals x squared plus cotangent of x. So the first part should be easy. And then the question is, what do you do with cotangent of x? Well, I can see 3 different strategies. One is, you memorize it. Okay, you forgot to memorize it. 2, well, I hope you know what cotangent is. Cosine of x over sine of x. Use the quotient rule, just like I did with tangents. Third way is, and this is probably a ridiculous way, but you remember that the derivative of the tangent is the secant squared. And then you think, what's the derivative of 1 over the tangent of x? Well, that's the derivative of the tangent to the negative 1. I don't mean inverse here, I mean, I guess I should. Only my fingers were made of eraser material. No, that's not what I wanted. I wanted the opposite from this one. Okay, so now I can use the chain rule. Okay, so this is negative 1 tangent of x inverse, not inverse, to the negative 1, to the negative 2. That's my power rule, times the derivative of the tangent. the secant squared. What's that? -1 over, I gotta write this as, write it out. Sine of x, cosine of x squared times 1 over cosine squared x. No, 1 over sine squared x. That's the secant squared. And what does that turn out to be? -1 times, at the bottom I have sine squared x. I bring this up, so I flip it. Cosine squared. Oh, that's not right. How do you do that? Secant squared is the cosine squared. I'll get it right. Flip this, so this is cosine of x over sine of x squared. The cosines cancel, I get -1 over sine squared of x. And that's minus the cosecant squared of x. I guess it's time for a break. Before you go, for the break, a little announcement about office hours. If anyone needs or wants me to be in my office today after class, I will. Tuesday is a complication. I'm going to proctor someone's exam around that time. I usually have office hours. So if you want to see me, I can see you after that class. I think it probably goes from 12:15 to maybe 1:30-ish. If you want to see me, then let me know. I'll find the exact time. And I'm also available this weekend if you want to do a Zoom about stuff. That Wednesday will probably be, everybody will be asking me questions, hopefully not. And of course, you need to be prepared for the midterm on Thursday. So, all right. Why don't you take a break and we'll move on.
Why did you have to do all that?
I could have just done that. I could have just memorized it. It's the minus cosecant of x. I'm just showing you there's different ways to get there, depending upon what you remember.
So it would be what?
It's the same answer. If you memorize it, its derivative is negative cosecant squared x. Oh, I don't know why. Okay, let's flip it. All right.
Well, why can't you do cosine of x over sine of x? Can't you do that?
Cosine of x
Yeah,
over,
like leave it like that. Can you do that or not?
we want to find this,
Yeah?
right? Why can't we leave it like this?
Yeah, over sine of x.
Well, that's the cotangent, so we need to find the derivative.
Oh, I know that.
We need to find the derivative.
I get it, yeah.
Okay. All right. I'll be back in a couple minutes. Judy, are you gonna see Lisa? Are you gonna see Lisa?
Leave it to me, maybe.
Oh, all right. I'm not gonna give it to you, it's just gonna be.
I don't see anything.
Okay, we're going to move on to the next section. I guess I should repeat this material today and on Tuesday will not be on the exam. There's a review sheet online in the file section which had an error in it. Michael helped me find the error on Tuesday, so I've updated it. If you downloaded it before then, you can go look for the error. It's in the first problem. It's a minor error. So we've been talking about, functions and their derivatives. And we've talked about the idea that the derivative describes a rate of change. If the x-axis is time, and it's definitely a rate of change in time. There are other kinds of, we can have changes relative to other variables. And we've talked about the chain rule. Which explains how you have two functions and you know their derivatives, how to combine their derivatives to find the derivative of the composed function. So, what we have is a composed function whose derivative is related in some way to the individual rates. And that's the subject of today. We're going to be going into a section now where we do some applications that are using this great tool we have of a derivative, finding a derivative. Some of these are nicely, they're real world kind of problems, although they may be a little idealized. There are things like this you're going to run into in many of your subjects, economics, physics, engineering, even computer science. I think this will come up. So these problems, we're going to do a few examples. We're going to show you how to do this by doing some example problems. Again, these are somewhat simplified in a way. What makes these problems difficult and what people stumble over is their background in math. because typically it's geometry we're dealing with. So just as a super simple example, if you had a pipe that is connected, you have a small pipe and a big pipe, and you're pushing fluid through the pipe at a certain fixed rate, you know that the fluid is going to move a certain distance through the smaller pipe in a certain time, but through the bigger pipe, it's going to move a smaller distance because the pipe is bigger. So these rates are related in some way. Now, in this case, I think should be clear, it's just going to be a constant. It's going to be some number that's going to describe the difference between the rate here and the rate here. It's going to be related to the cross-section of the pipes. But with calculus, we can do problems that have this kind of rate of change that is somewhat more complicated. So, first problem we're going to do has to do with blowing up a balloon. So we have, don't think like, the kind of thing you would get at a circus. Think, you're a weather guy. What's the name of that subject? Meteorologist. You're a meteorologist, and you're going to put up a weather balloon, and you hook it up to a tank of gas. A little wheel. Open up, and you start filling it up at a constant rate. 100 cubic centimeters per second. As we fill it up, the radius of the balloon, this perfectly spherical balloon, increases at some rate. This is a fixed rate, but this rate is not fixed. And we want to know what that rate is. And in particular, we want to know how fast it's increasing, how fast the radius is increasing when it's equal to 25 centimeters. Okay, that's, think about the problem a little. You're filling up with gas at a constant rate. The radius is getting bigger, but clearly, for each distance the radius increases in one dimension, the volume's increasing a greater amount, right? So actually, since this is constant, the rate at which the radius is growing is going to get slower and slower. At least that's what we expect. So to do these problems, there's a pretty straightforward way to go about it using the chain rule. Chain rule, and it's usually convenient to put this in the Leibniz notation. dy dx equals dy du dx times du dx. Or, in the case of this particular example, it might be convenient to say the change in volume with respect to time is equal to the change in volume with respect to radius times the change in radius with respect to time. Now, looking at this and looking at the problem, we want to equate these, right? The r dt, that's actually what we want to find. The v dt, well, that's our 100 centimeter cubed per second. So really, we know, this is the unknown. We have this. So this is what we have to figure out, dV/dr. Well, what do we know about the volume of a sphere with respect to radius? Does anyone recall the formula?
3/4 pi r cubed.
Yes, thank you. Well, knowing that, we can almost be dumb about this. We can just be very mechanical. What's dV/dr?
Is it 4/3 or just 3/4?
Thank you. Anyone? This is just a monomial power rule, right? I wonder if it's scary because it's not x and we've got this pi in here. I wrote it 4/3 pi, this is a constant, r cubed. So if I want ddx x cubed, what do I get? What's the derivative of x cubed?
X squared.
3x squared. So this is just 4/3 pi times 3r squared. 3's cancel. So we have 4 pi r squared. Okay, well, now let's plug everything into this equation and see what we get. So dV dt, that's 100 centimeters cubed per second. I'm going to try and keep the units in here, because if the units don't work out, we know we made some kind of mistake. Times 4 pi r squared, that's that doesn't look right. dr. I think it's okay, but it just doesn't feel good. Yeah, something's wrong here. Oh, I see what's wrong. I'm going to put the equal sign in the right place. There we go. Times dr dt, which that's what we're looking for, so I'm just going to call it x. So x is equal to 100 centimeters cubed per second over 4 pi r squared centimeters squared. And we're going to end up with 100 over 4 pi r squared centimeters per second. That's what I wanted to see. Because centimeters per second is exactly what's happening to the balloon's radius. it's at a linear velocity. All right, so that's half the problem. We now know this is the rate. It looks copacetic. As r gets bigger, the rate gets slow. You know, the rate that the radius is increasing gets slower. Not that you can do this with a balloon, but if you reversed it in time, you know, if you kind of let r go down to 0, it's like the rate gets infinite. We have to kind of start it off at an infinite rate, but for an infinite amount of time. Okay, so the only thing left is what's the numerical number we're looking for? Well, at the point where the radius is 25 centimeters, that's when we want to know the rate. So that's 25 is 100 over 4 times 25 squared times pi. 4 times 1 to the 25 is equal to 100, so it's 1 over 25 pi. Centimeters per second. All right, so this is a typical related rates problem. They come in a few varieties, and we'll take a look at some more of them. Any questions about this so far? Once you've done a few of them, you get an opportunity to do with the homework. They start to fall into place. Again, usually this is the issue. You have to understand the geometry of it and remember some of your geometric formulas. Okay, if I erase the board? No. Never?
Never yet.
Anybody still writing? All right.
Would you get mad at us if there was a problem like that on the test or whatever, and we didn't put the right units, or we didn't put units at all?
I wouldn't care. I mean, the reason I brought in the units is, well, actually I was writing it out and I made some kind of dopey mistake, and I was like, wait a minute. Multiplying centimeters times, I know that's not right. So it, gave me something to like hang my hat on and say, wait a minute, I'm doing something wrong. Caught my mistake. Now I don't want to put you on the spot. Your major is,
Oh, it's kind of in between right now.
well, give me the two ranges.
Computer science and bio, but I'm
Bio, okay.
moving towards computer science.
Okay, bio, a pure science. You're going to do a lot of knowing dimensional analysis, keeping track of the units. It's a valuable skill, especially if you get a number that seems really wrong and you maybe did the calculation right, but you didn't convert the units.
And you plug that into all your
25 centimeters.
I'm giving you a minute.
25 here.
the top is Oh, that's so easy.
I dropped it.
I got it.
Love that for you guys. I wish I was that smart before.
This one, the water.
All around.
All right. This is another typical related rates problem you see in a math class. I don't know why it's a ladder, it could be a board, or it could be a whole wall. But maybe it has something to do with the idea of industrial accidents. Somebody's climbing up a ladder and it's going to slip out and, you know, crash down and someone's going to hurt themselves. But I don't know why. So the ladder is 10 feet long and it's leaning against the wall. And the bottom of the ladder is 6 feet away from the wall. And it's slipping. The top is coming down, the bottom is going out. And we want to find how fast it's going. We get to use the usual coordinates, x, y coordinates. So really, we're looking for the x dt here. And we're given that, oh, I'm wrong. That's wrong. We're given that it's slipping 4 feet per second. Now, physics majors out here, you know this is highly unlikely. Maybe if you had a little contraption here that was moving it out on, 4 feet per second. Just, your intuition is as it starts sliding out, it's going to speed up because gravity's, pulling it down. But this is the problem. It's moving out at 4 feet per second. I guess you could do this like on a Hollywood set. You have a mechanism set up to work this way. So the question is, how fast is it sliding down? Well, here we have a rate, and here we have a related rate. So what we have to think about is, how are they related? This is the difficult part, and thankfully you're going to know from now on how to do it in a ladder problem. Here we have the x and the y, and we know, and this is 10 feet, and we know how to relate these. It's just the Pythagorean theorem, right? X squared plus y squared equals 100. And we have, as a given, the rate this is moving. That's our dx dt. That's 4 feet per second. And what do we want here? We want to find dy dt. Well, we've seen something like this before, where you want to find dy dt, but you have it. It's not a function. We're just going to use implicit differentiation. With all those tools becoming useful. So find the derivative. The derivative with respect to x. This is 2x. The derivative with respect to x of y is 2y y prime. That's the chain rule coming in here. And the derivative of 100 is 0. So now we can solve for y prime. Y prime equals negative 2x over 2y, or negative x over y. And what else do they give us? They want to know how fast it's falling when what rate is it falling when the bottom is 6 feet from the wall? Well, that's nice. They're using the same axis we're using. Well, we know this is negative x over 6. What's x when y is 6? 6, 10. Okay, now, I know you've all taken, actually I don't know that. Maybe they don't require the SATs anymore. Some of you have taken the SATs, did the geometry part, and if you were good at it, you probably recognize this ratio. It'd be easier if I wrote it this way. It'd also be easier if I drew it more in perspective. Well, yes, this is maybe a little further. Everyone recognize this triangle for what it is? Yeah, 3, 4, 5 right triangle. So what's this going to be? 6, 10, it's going to be 8, right? Similar triangle, even though it doesn't look it. So y equals negative 8 over 6, or negative 4/3. What is this telling us? Negative 4/3 feet per second. And it's negative because it's going down. So that's kind of the latter problem. You don't remember the Pythagorean theorem, or you don't remember how to, well, you don't actually, we could solve for y and differentiate. What would we get? You get y equals square root of 100 minus x squared. So the derivative is going to be 1 over 2 to the square root of minus x squared times negative 2x. That's the chain rule. And here they're doing that calculation I did here for you. All right. The next problem is probably as difficult a one as you will find in the homework. Again, what makes it difficult is not the calculus, not the related rates, it's the geometry. And again, you just have to do the homework on these and practice it a little and get your confidence up and not get too frightened. I mean, you haven't taken a midterm with me, but I try not to give problems that are just scary for no reason. I mean, if the concept is hard and kind of frightening, I can't help that, but there's no reason to make problems particularly scary. Okay, so this is the, I don't know, the snow cone, or the conical tank problem. We have a tank. It's a base radius of 2 and height of 4. So at the top it's 2, and its height is 4. And it has some liquid in it. And I don't know, we have some kind of inlet here. We're pouring water in. And the level is rising. We'll call that level H, right, wherever the water is. And, we've had some kind of valve here, but 2 meters cubed per second. That's how quickly the water or fluid is going in. And we want to know how fast it's rising, how fast the level is rising in general, but in particular when h equals 3 feet. All right, this looks kind of scary, but we kind of mechanically repeat what we did before. We say volume with respect to time, the change in volume with respect to time is the change in volume with respect to height times the change in height with respect to time. Okay? I mean, those seem to be the rates we're dealing with. How fast the height is going, what the volume is. So this part, what about dV dt, the volume inside the cone? Where does that come from? Oh, you raised your hand. Oh, sorry. Any ideas? You have to think about this a little. You have, we're here at university. We're not, you have to squeeze stuff out of the brain. We gave you the Lou?
There was like a computer science homework and they gave us like the formula so we didn't have to actually load the formula for the column.
We'll get to the formula for the cone.
No.
That's okay. We'll get to that. Just what's the change in volume with respect to time, with respect to this problem? We got to put the pieces together. Anything look like a volume up there?
The meters cubed a second.
Yeah, this is just 2 meters cubed per second. Okay. dH dt, that sounds familiar. Let me read the problem. A water tank in the shape of an inverted cone, sometimes you have to read these things over a few times for them to sink in, has a base radius of 2 and a height of 4. Water enters the tank at a rate of 2 meters cubed per second. How fast is the water rising How fast is the water rising when the water is 3 meters deep? Doesn't that sound like change in height with respect to time? Yeah, that's our unknowns. That's what we want to find. So what we really need here is dV dH, the change in volume with respect to h. Well, that means we want to know what the volume is with respect to h. And therein lies the stumbling block of geometry. So now we have to think about the volume of a cone. So if a cone has a radius of r and a height of h, anyone remember the formula? Yes?
Is it pi r squared over, h divided by 3?
Absolutely is. It's a little like a pyramid, well, it's upside down pyramid. It's like a pyramid. It's the base area, which is pi r squared. Oh, did you say h?
Yeah.
Yeah, okay. Times the height, but because it's, you know, a pyramid or a cone, 1/3. Okay, so pi h r squared over 3, so dv dt, no, dv dr, right? That's what we want. Oh, dv dh, that's what we need, okay. What's dv dh? I think this is confusing because there's a lot of letters here. Pi is just a constant like 3, so we can ignore that. R is just, you know, whatever the radius is. Oh, wait a minute, hold on. I'm gonna have to think about this. The radius at the top of this thing is 2, when the height is 4. What's the radius when the height is h?
I mean, do you need that, or you just need the rate of fill in the area?
I mean, I was about to make a terrible mistake and go, well, R, well, it's not H. It's not a constant, though, is it? We got to find out what R is, you know, when the height is H. Any thoughts on this? I'm going to draw a little diagram here. So this is 2, 2. This is 4. This is H. We want to know R. Now, this is where everything you forgot becomes a problem. Because this is a really easy geometry problem. Where's H? So I have two similar triangles here. There's one, there's another. I didn't draw it very well. This is 2, this is 4, this is H, this is R. What do we know about similar triangles? What did we forget about similar triangles? They're proportionate. So we have 2 over 4 equals R over H. No, I got 3 minutes. Okay, so really, we want this in terms of H, right? But we have an R. Well, okay, 2H equals 4R, or H equals 2, H equals 2R. No, I want to solve for R. R equals 1/2 H. So I can plug in here pi H 1/2 H squared over 3. That's pi H cubed over 12. And dv dh then becomes pi H squared over 4. Call this x. And now I have the solution to my problem. You know, my dHdt, my x, is pi squared over 4 divided by 2 liters cubed per second. I'm not going to worry about the unit. And if I plug in h, what was the problem? 3 meters deep, then I get my answer. And this is hard because you have to see this ratio problem from geometry. You need the volume from geometry. And again, we use the chain rule and put it together. I expect when you work on the homework for this, don't feel like it's more important than getting ready for the midterm. Turn it in late, that's okay. But when you go over it, you have trouble the day after the midterm, please bring in questions about these. Definitely take some effort on your part. Figure out how to do these.